I often ask you to build circuits involving memory to a specification. And here's a simple example. I want to build a toggle flip-flop, TFF. It's a bit like a D flip-flop, but it behaves according to a different logic. It has one control signal coming in, and it has a 1-bit memory that ought to be loopable, and it behaves as follows. If the control signal is 0, then the contents of memory should stay the same. Whereas if the control signal is 1, the bit stored in the memory should flip. So, what's our circuit going to be like? It's going to be built from a D flip-flop, because that's our main source of memory, with a clock signal that I don't need to wire up, and it's going to produce an output called Q. Meanwhile, there's going to be some input to the whole thing called capital T. But because of the D flip-flop being a memory, I'm also allowed to loop the Q signal back round. I can use what's currently in the memory in order to compute the control signal D that drives the D flip-flop. And remember what a D flip-flop does. Q at the next step is exactly D at the current step. So, what goes in this gap? Well, let's figure it out the way we usually figure these things out. Let's write a truth table, but now a truth table for time signals. We know what's in memory at a given time t, any time t. And we know what the control signal is at that time. So we should be able to tabulate all of those situations. Memory is either holding a 0 or a 1, and the control signal is either 0 or 1. And now we need to figure out what we would like to be in the memory at the next time step. That's Q of t plus 1. And we do that in accordance with the logic of the specification. That's to say, if the input is 0, so here the input is 0, memory should stay the same. Memory is currently 0, so 0. If the input is 1, we have to toggle the memory. So when it starts with 0, it becomes 1. Likewise, here we have the instruction stay the same. Memory is currently 1, so it stays 1. Here the instruction is toggle, and the memory is currently 1, so it becomes 0. So we figured out the behavior we want. Now we have to figure out the appropriate D signal to send in at time t to get the behavior that we want. But fortunately for us, the D flip-flop obeys a very simple equation. What comes out at time t plus 1 is what goes in at time t. So this is exactly the truth table for the D component we need, and here's Q of t, and here's t at any given time, the control signal t. So this is exactly the truth table for the component that goes in this hole, and we should recognize it straight away as being an exclusive OR gate. So we've got a plan. We turned the specification into a truth table for the desired behavior, and then we figured out the control signal which would deliver the desired behavior, and that told us how to build the right logic for the control signal in terms of the old value of Q and the current input of the control signal capital T. But don't take my word for it. Let's do that in syrup by the magic of editing.
Let's code that circuit up in syrup. What did we say? That TFF should take a controlled signal in and give us a loopy bit back out. That means that the output should be determined only by a memory. That's fine, because the plan is that we get in our control signal T and we give out our memory Q, where Q is exactly given by a D flip-flop controlled by D. And what did we figure out on the board? That D should be given by the exclusive OR of Q and T. So let's see if that's acceptable as a definition. Yes, it's defined. It's checked the right connectivity, and it has also checked that this Q, which is looped, is given only by a memory. There's no direct dependency on the control signal T. Now we can do an experiment just to ask, what does the T flip-flop do? And when we run the experiment, you'll see that we are shown what happens inside the flip-flop for each possible control signal and state of the memory. So you can see here when T is 0, that the memory stays the same, and moreover that the output is the same as how the memory starts. Meanwhile, when the control signal is 1, again the output is exactly what's in memory, but what happens inside the memory is that the memory toggles. So we have correctly delivered a T flip-flop given a D flip-flop.